right, so what that does is that brings us to a way to graph all of this. All of this information can be kind of condensed into a graph. And this graph is called a heating and cooling curve. You will be creating your own heating and cooling curves in the lab this week with the use of a chemical with a very low boiling point and melting point. And we know that that type of chemical is going to have very weak intermolecular forces. And what we found that no matter what chemical we use, the heating and cooling curves will always have the same shape. So they may occur at different temperatures with different heat values, but the shape will always be the same. So understanding how to read a heating and cooling curve is extremely important, and to be able to articulate what is happening at each point in the graph is also extremely important. So what we're going to do is we're going to look at each of these, and I'm going to explain what is going on. So you can see it kind of looks like a staircase. It is always going to be in the staircase shape when you look at a heating and cooling curve. So at the point of increase, so here you have a solid. In this part you have a liquid, and in this part you have a gas. So there are your three phases. So they are going to make the incline of your step shape. At this point, this is when the solid is present, the liquid is present, or the gas is present. When you increase the temperature at these points in the graph, okay, so at these points in the graph, the temperature being added is being used to raise the temperature of the substance. So at each of these inclines, when you add heat, the temperature is being used to raise the temperature. We can calculate the heat being produced or inserted by an equation called the MCAT equation. So this is the mass times its specific heat times its change in temperature. Now, I'm not going to make you calculate that right now. Eventually, we will be able to. But if you were looking for the heat, the amount of energy in those particular areas of the graph, that is the equation that we would use. So the main thing to understand here is that the heat being applied is being used to raise the temperature of the substance. So we are raising the temperature of the substance. So in each of those areas, substance. So in each of those areas, that's what is occurring. So as we're adding heat in the inclined portions of the graph, we are using that to raise the actual temperature of the substance. All right, so that brings us to the flat areas. All right, the flat areas are where our actual melting and our actual vaporization is occurring. So at this point in the graph, your states of matter are in equilibrium with one another. So in the flat portions of the graph, so in this area here, the solid is in equilibrium with its liquid. So you have both phases present. In this area of the curve, you have both the liquid and the gas present. So they are in equilibrium with one another. So what this means is the heat being applied, if you notice, you're not increasing the temperature. So in these areas, the temperature is not being increased. The energy being applied, the temperature or the heat being applied at this area is not being used to raise the temperature of the substance, but it's using the energy to overcome the attractive forces. So the attractive forces are being overcome by the added energy. The phase change is actually occurring in those moments. Okay, so in these areas of the graph, the phase change is actually occurring. So the heat or energy being applied is not raising the actual temperature of the substance. It's being used to overcome those attractive forces to separate those particles so that it can become a gas or it can become a liquid. It also can occur in the reverse. The only difference, instead of adding heat, we are taking heat away. And that's why it's color-coded, with red being exothermic and blue being endothermic. Heat is being absorbed. So the heat of fusion, that's the calculations we're using at those points. So at the flat portions, Q, the amount of energy, is equal to the mass times either its heat of vaporization or its heat of fusion, depending on the process that is occurring. Now, also, if you're going in reverse, okay, so if I'm going to erase all of this here. So if I am going in this area, so I'm following the graph in this way, okay, all of my heat of fusion and heat of vaporization are going to be positive. Okay, so that number associated with the substance is going to be positive. But if I follow the graph in the opposite direction, so if I'm approaching the graph in this direction and I'm going backwards, all right, my values for my heat of vaporization and my heat of fusion are going to be negative. All right, so that's the takeaway from these graphs. So what you need to be able to do when you're looking at these graphs is you need to understand what is occurring at each section of the graph, and you need to be able to explain what is going on at those points.